It is a real pleasure to introduce Chris Burdzy, that will talk about billiards and PDEs via white noise. Chris?
Okay, it's a great pleasure to give talk in this seminar. To be honest, I would prefer to give this talk in person. I visited Brazil twice and Latin America a few more times. But well, I guess that's the best that we have right now. So anyhow, it's a great pleasure to give this talk. And actually, you will see that is double pleasure for me for a specific reason. So first of all, let me say a few words about the structure of this talk. I will start with mathematics, and I will end with speculation. So the first part will be mathematics in the usual sense of the word, namely, I'm going to present results that are proved and mostly published, and it's solid mathematics. Well, the bad thing about that is that it doesn't have any probability in it. It's all deterministic. But I present this as a motivation for the second part, which is probabilistic, and I want to somehow show you why I got interested in a certain model. And in the second part, well, that's my current project. So it will be a mixture of just a model, some simulations, some conjectures, and none of that is finished. And the reason why I'm doing this, at least one of the reasons, is that that project is in the area that I'm not familiar with, but I know that some people who are at this talk are familiar with. So I hope that I will get some help from you in terms of literature, existing literature. Anyhow, I'm going to start with billiards. So for some time I was working on billiards, but not in the sense of billiards theory. It's a little bit different. I'm sort of, in some sense, real billiards. What mathematicians call billiards theory is the theory for a single point particle moving and reflecting from walls of a table. And here I'm talking about real billiards. So consider n billiards in the dimensional Euclidean space, but there are no walls. So the balls only reflect from each other. And I will assume, to make things simple, that they have the same radii, equal masses, and the collisions are totally elastic. So the energy and momentum are conserved. Now, I will be interested in the number of collisions. So in this simple picture, what you see is one ball, A, traveling here, and it collided with two other balls, both B and C. So in this particular billiard evolution, we have two collisions. And I will start this talk with a public opinion poll. How many collisions can you get with three balls? So at three balls, you can choose any initial conditions, any positions, any velocities. And well, let's see, you can either type in chat or say in voice, what is the maximum possible number of collisions of three balls? What's your guess? Please don't be shy. I mean, this is not mathematics. This is just a guess. But certainly two. Can you get more than two?
6? I don't know.
Okay, Pablo says 6. Milton says 5. 3. Okay.
Can't you get unlimited one by pressing one with the 2 on the side and letting it bounce between the two?
Did you say infinite?
Oh, unlimited.
Unlimited. Okay, so there's another suggestion, unlimited. Okay, so we have another of, so the concrete numbers were 3, 5, 6. And then there is a suggestion that it might be perhaps unlimited. Okay, so I will give you an answer, but before that, let me say a word about history. So it is relatively easy to see that you can get 3 in 1 dimension if they are all just on a line. And then Uhlenbeck apparently thought that would be the maximum because the 1 dimension is the most constrained, whatever that means. And I find it interesting that Sinai went in the other direction. He sort of suggested this was a question, not a conjecture, but he said, well, can one get actually an infinite number of collisions with not necessarily with 3 balls, but with a certain number of balls, some number of balls. So Uhlenbeck thought that it would be sort of typically very small, and Sinai thought that it would be very large. So let K and D be the supremum of the number of collisions for n balls in d dimensions. That's the notation. Well, it turns out that in 1 dimension, there's a rather easy argument. It says that it is n times n minus 1 over 2, or if you wish, this is n choose 2. So this is the number of pairs of balls, and actually this is not a coincidence. But the 1-dimensional case is very special. And the argument that I'm not going to give you, you can try to think about it yourself. It's not hard. But it doesn't, the same argument doesn't work in higher dimensions. So it was actually quite a substantial theorem, a very impressive theorem by Wasserstein in 79, that the number of collisions is always finite. And to this day, there is no trivial proof of that. All the proofs are quite elaborate. So that was 79. And then 20 years later, there was a spectacular article by Buragov, Verleger, and Kononenko. They actually gave an upper bound. It's absolutely explicit. Now, I wonder if you've noticed that the bound does not contain a D, but somehow the fact that it doesn't contain D is not that significant, because in some sense, the independence from D is not that hard. The bound is extremely it is hard. It's hard. It's a hard argument. And now you may see that I also express the theorem, the inequality, in the terms of logarithm, because somehow these bounds that I'm going to present to you look better on the logarithmic scale. So it is about n squared log n, the upper bound on the logarithmic scale. So I have a new paper, and in my paper, I have a new bound, which is on the logarithmic scale. It is n log n, but I had to pay a price, namely my bound depends on the dimension. So if you fix a dimension, it is n log n. And also, if you look at my bound without logarithms, you will see that it's very complicated. So I find it sort of amusing because all my life I worked on Brownian motion, some analysis, and there were lots of bounds that had the form C, epsilon, delta. These were some absolute constants, but nobody cared about them. Nobody tried to calculate them. But somehow in this field, if you are able to find a bound, then somehow automatically it's explicit. And I find it amusing because this is new to me, that actually you do not get some C or epsilon or n goes to infinity. Well, you just get an absolutely explicit bound. Okay, so these are upper bounds. How about the lower bounds? Well, the 1-dimensional case is easy, and then in d dimensions you will get at least the same number of collisions, because in high dimensions you can also arrange balls on a line. There are centers on a line. And now you have the answer about 3 balls. Actually, it's 4. In 3 dimensions you get only 3 collisions in 2 dimensions, you get 4, and then higher dimensions will not help you. So 3 balls can have 4 collisions. And once again, I'm not going to show you the proof. You can just try, yourself to arrange the 3 balls and find initial conditions so that you get 4 collisions. And once you get 4 collisions, I can assure you that that's it. This really goes back to a student in the 60s, but then it was published later. So I've noticed that there was no lower bound, and I worked with Mauricio Duarte, and what we got is n cubed. So we went up from n squared to n cubed. And very soon that was improved to the exponential bound. I say very soon, but you may look at the dates, and it looks like our paper was later. So for us, 2019 is the date of publication. For them, it is the date when they submitted it to arXiv. And I have not seen published version of their paper yet. So they improved our bound, and well, I guess it's waiting for being published. These are the same bounds. The only thing is that they added the logarithmic version for Burago and Ivanov's bound. So this is Cn on the logarithmic scale. And well, this is the current state of the art. So I guess I should add that this is to be clear about that. This is for d greater or equal to 3. You see, for reasons that I will not go into, it turns out that our bound with Mauricio Duarte is still the best in 2 dimensions. So there's this intriguing possibility that the bounds in 1 dimension and 2 dimension and 3 dimensions are all different. But when you go from D to higher dimensions, it's the same bound. Now, Serre thought about significant collisions. You see, you could have what some people call grazing collisions, when one ball just barely touches the other ball. And these are sort of feel insignificant. You can have lots of them, but they don't mean anything somehow. So he thought about significant collisions. I'm not going to define that because it's a little bit technical, but you can believe me that this is a sort of reasonable definition. It says that there is a certain amount of energy exchanged, and that energy is sort of comparable to the total energy of the system. So it's like a non-trivial collision in some sense. It's a little bit more complicated than that. And actually his bound depends also on the parameter, because I said a certain amount of energy. Well, how much energy? So it's more complicated, but this is an honest account of his results. It's more complicated, but basically he says that only n squared. So what this means is that all those exponential, that exponential number of collisions, so most of these collisions are negligible. Even in our bound, which is only n cubed, most of the collisions are insignificant in some sense. Okay. So this is how I got interested in this model. I call it pinned billiard balls. So let's have a look. Let's have a look at the left picture. These balls are in a very tight configuration, and one way to think about them is that the distances between them are, say, 1/1,000,000th of the diameter. So you wouldn't see it in the picture. There's no way. The distance is so small. But actually, in the mathematical model, I pushed it to the limit, and the distances are 0. And the balls are not moving. The idea here is the following. When the configuration is very, very tight, then the collisions would happen so fast, so many of them, that you would not see any significant change in the positions. So somehow in the limit, the positions are fixed. Before I go any further, let me tell you why I'm interested in this. There are both intuitive and theoretical reasons to think that this is the configuration when you get the largest possible number of collisions. Some kind of tight configuration. In other words, if billiard balls fly like planets and meteors and asteroids very far from each other, then you will not get many collisions. They really have to be tight, like, I don't know, in a star or in a supernova explosion. And then you will get lots of collisions. So, well, that's the intuition. So now I claim that these balls do not move. This is why I call them pinned, but, well, then it looks like there's nothing to talk about, right? Well, I make them collide. So first of all, I give them velocities. So all these red arrows are velocities, although I guess, strictly speaking, I should call them pseudo-velocities. There are no true velocities here. These are some kind of vectors. And since they don't move, I have to, there must be some exogenous process that says which balls collide. So I choose a pair, and I tell them to collide. And then the velocities change like in a real collision. So there will be new vectors. The balls are not going to move anywhere, but there will be new vectors like after collision. And then I choose another pair randomly, uniformly. But in this case, please note that the vectors are pointing away from each other, which means that if these balls could move, they would move away from each other, and the velocities would not change. So they don't change. And also, if I choose some balls that are not touching, then once again, like in the case of moving balls, that there will be no collision. And this is going on. And after some time, you get a configuration like in the right picture, in the picture on the right. And there will be no more collisions, because all these vectors are such that if I choose any pair of balls, and it's not clear in some cases, like, would these balls collide or not? Well, it's not obvious, so you have to trust me, or rather trust my program. My program checked, and no, these balls would not collide. So this is like some kind of terminal configuration of velocities. So this can actually be proved. So for any number of balls, any dimension, any any positions do not change, but I can choose them, right? And any collision order. So any collision order, this is not actually a probabilistic statement. This is a deterministic statement. No matter what collision order you choose, the number of collisions will be finite. So in that paper with Jaya Devasraya and Mauricio Durarte, we had some bounds, but they depended on positions. So now I have a new forthcoming paper. It's basically finished. We are just polishing it at this point. We have a bound. And I don't know if you've noticed, but this is, I express this only in the logarithmic terms so that I don't bother you with an explicit formula. And I wonder if you've noticed that these bounds are exactly the same as for the moving balls. Well, this is, of course, not that surprising because it's a sort of a variation of the model. But let me say that none of the results implies the other. There is no monotonicity here in the sense that the number of collisions that you can have in one model with moving balls and in the model with balls that are not moving implies the other. So there is no logical implication. It just happens that these are similar models, similar bounds. Let me also make a comment now about some elements of these bounds. So there is Cn squared here and Cdn. So actually, this is easy to explain, not easy to prove, but easy to explain. You see, Cn squared is simply the total number of pairs of balls. Well, if you have n balls, that the total number of pairs is n choose 2, which is on the order of n squared. Or if you fix the dimension, it is simply linear in the number of balls. That is not that easy to prove for moving balls, but well, at least I can tell you the meaning of this part of the estimate. Concerning that log n, I don't have a good explanation. These are very complicated arguments. And it just happens is that although they are completely different, in this case, pinned balls, and in the case of moving balls, you get that log n. So who knows, maybe it's correct, but this is a bound only. Okay, so now let's consider the situation when you have not just a few balls, but a very large number of balls. So from now on, from the rest of the talk, I will be interested in those configurations where you have a very large number of balls. So in the picture on the left, you will see, well, I don't know, I hope that you can see small black dots. If you don't see black dots, then don't worry. The black dots are centers of balls. I did not draw the balls because there are so many of balls and the picture would be so crowded that you just have to believe me that there are lots of balls on the left. And they are arranged in this circular clump. So the black dots are the centers, and I hope that you can see red line segments. Red line segments represent velocities. And these are initial velocities. So in this simulation, I used white noise. What I mean by white noise is IID, two-dimensional normal distribution. So these are IID, two-dimensional normal, but rotation invariant. And then, this is a simulation. I chose pairs randomly, and what you see on the right-hand side is the terminal configuration, and it looks like it's ordered in a very nice way with very small velocities at the center, and then large velocities pointing away from the center on the outside. So now let me show you another simulation with different initial conditions. So this initial condition, you do not see the initial condition because you already see the initial stage of the evolution. So the initial condition was 0 everywhere. So all velocities were 0 everywhere. And there was just a single ball with non-zero velocity. So like an explosion in the middle of some, I don't know, material, some gas or whatever. And what you see here is what happened after some initial time. So you see that the energy is spreading, and I think that you can see that there are some vectors that are very long, right? So it means that some balls have very large energy, and well, it's spreading. So on the right, what you see is the next stage, sort of like the middle stage of the evolution. So obviously, well, I don't know if obviously, but I hope that you can see on your screen that there is a lot of activity over here. This is like where the most of energy is. And there isn't very much left at the center. And somehow it has not reached the boundary yet. And then the picture on the left is the same as the picture on the previous slide. So after some time, you once again have perfectly ordered configuration. And by perfectly ordered, I mean that all, there are no more collisions possible. So it means that the velocity have to be ordered in a suitable way so that these balls cannot collide anymore. So all velocities point away from the center, and they are larger close to the boundary. Okay, so right now I'm talking about joint project with a number of people. I listed 3 of them. There will be probably more. When we did simulations, we noticed sort of 3 kind of macroscopic phenomena. So order to noise to order is, well, what I have just shown you. Then traveling wave, well, it is sort of, I don't know how obvious it is from these pictures. And then freezing at the boundary. So what I want to do next is I want to share a different picture with a different window. So I want to show you Mathematica Simulations. So these simulations are in 1 dimension. And the interpretation is the following. You see on the horizontal scale, you see, it goes from 0 to 2000. It means that there are 2000 balls on a line. And you see this line. So these are initial velocities. And velocities on the left are positive. It means that all these balls are trying to get to the center. The velocities on the right are negative. So all these balls are trying to get to the center also. And the farther away you are, the velocity is larger, which means that every pair of balls can collide, because the ball that is farther away from the center is sort of faster than the ball that is closer. So let's see what happens. And this is what you would expect in the end, because the velocities have to be ordered, right? The final configuration has to be ordered because I claim that there are no more collisions. So not only monotone, it has to be increasing. It is less obvious that you will go from a straight line to a straight line. Okay, now let's go to the next picture. You see, this is not the first frame. So actually, in the first frame, there was no tail on the left like this. So, and this tail requires some extra commentary. So let's have a look at this evolution. So you see, there's an obvious wave going to the right, and in a sense, it should be that way because originally, the velocities were on the positive side. So it means that the balls, in some sense, wanted to go to the right. Well, the balls cannot move, but the velocities can move. And a commentary about this tail. So if I have time, I will explain to you where this comes from. And this tail looks really large, but it contains only 5% of the energy. So in some sense, it's negligible. The wave is the interesting part. And finally, I want to show you a simulation that started from white noise. So white noise here simply means IID normal. There, all these values, all these points are IID normal. And let's have a look at the simulation. Okay, so this illustrates freezing. Please note what's happening at the end points of the interval. You see, there's more and more of freezing. By freezing, I mean that there's no noise anymore, and essentially the shape becomes fixed, the shape of the curve. So we have this freezing effect. Of course, this is a simulation, so this is not perfect. You see still some noise here, but well, that's the idea. Okay. So I'm going to stop sharing this screen, and I'm going to go back to my PDF presentation. Okay, so I hope that you can see it now. Okay. So here's my guess. So as I said, at this point, there is no mathematics. This is all speculation. So what we see here is white noise, but I call it modulated white noise. I don't know if there is an already known name for this kind of model. So if there is a name, you can tell me either now or later. So modulated white noise means that I multiply it by sigma, which is standard deviation, and by mu. Oops. Okay, so this didn't work. So let me say a few words about this. Why it is white noise? This is white noise, but it's my guess that it's white noise. First of all, you can look at the simulation and you can check the values and the correlations and so on. And the reason is that when the energy is redistributed, then the sum of squares is conserved. The conservation of energy means that the sum of squares is conserved. So what this means is that you're on a sphere, and if you're on a high-dimensional sphere, then the individual components or coordinates are ID Gaussian. So that's a hand-waving justification for white noise. And another justification comes from the microcanonical ensemble formula, because if you have moving balls, then the microcanonical ensemble formula gives the same energy. Well, it makes what all velocities IID, not IID, the joint distribution of all velocities in the microcanonical ensemble formula is uniform on the sphere. So it's the same thing. Then the coordinates are more or less IID normal. Okay, so it looks like I lost that slide. Well, I hope that. Okay, so my guess is that they are deterministic. And this formula is probably the closest to a theorem in this part, because it required some calculations that were, at least for me, that were non-trivial. And it looks like these functions satisfy these equations. So the evolution of mu in time is given by the gradient of sigma. Sigma is a scalar, and then the evolution of sigma is governed by the divergence of mu. So I will have some comments on these equations. But before I do that, I want to discuss this conjecture, because from my perspective, this is in some sense where I want to go. I would like this project to go in this direction. You might remember that I started with estimates for the number of collisions of balls, billiard balls. But all the estimates were, for the maximum possible number of collisions. And there was this estimate of Serre, who said that no. What he said is that the number of significant collisions is at most n squared, which means that all those estimates for the maximum possible number are not realistic. you will not get that many collisions that are significant. But significant is not the same as typical, because significant could happen in a very untypical evolution. So it's not quite the same. And here I believe that this model gives me at least a possibility of even defining what typically means. Typical means that we would start with a reasonable mu and sigma, some smooth functions, and some kind of reasonable evolution until all velocities are ordered. So I would love to prove a theorem like this, and at least at this point, I think that I have at least a way to stating a conjecture. And now I want to make a remark about this conjecture. So please know that n to the power 1 plus 1 over d is always less or equal to 2. For d equal 1, it is, that would be n to the power 2. And this is this is a decreasing function of d. This is counterintuitive because you can always go into higher dimension and place balls on a hyperplane. And they can evolve on a hyperplane. So how can you get fewer collisions in higher dimensions? But you see, the crucial word here is typically, because if you go to a dimension d and you place balls on a d minus 1 dimensional hyperplane, that's not typical. By typical, I mean some kind of a clump, d-dimensional clump, d-dimensional space. And then my conjecture is that it would be n to the power 1 plus 1 over d. But as I say, at this point, this is just a wishful thinking. And, I would very much hope to, well, that's my dream to prove something of this type. Okay, so, if these equations lead to a wave equation for sigma. If you combine them, if you do an extra, if you take an extra derivative, and if you combine them, then what you will get is this equation. So in some sense, this explains, this phenomenon that you saw in the simulations. Okay, so these equations are known. So what I've seen, and this is where I'm very uncertain, because I know very little about this field. I've seen these equations, for example, representing density and current in some other context. And I mentioned here books by Spohn and Kipnis and Landim, just because I'm searching, so I'm trying to learn things about this theory. I'm not suggesting that I know these books. And here's one concrete thing that I don't know. You see, in my case, I'm suggesting that these equations should apply to the moments of Gaussian processes, and that I have not seen. So if this is the case, then I would appreciate your advice if you've seen these equations representing the mean and standard deviation of a Gaussian process. So I would be interested in knowing in what context this was applied. Now, there is something perhaps special in this case. Namely, we have freezing. In this model, sigma represents the standard deviation, and it really has to be greater or equal to 0. I don't see how it can be negative in the model because, well, there's just no way in the model or in simulations to make it negative. So what this means is that sometimes there's this frozen region, and actually in that terminal situation, terminal configuration, sigma is 0 because there are no more collisions. So there is no noise. But this means that the problem becomes a free boundary problem because the equations apply sort of in different ways. There's this boundary between sigma that is strictly positive and sigma that is 0. And then this region, so this is the unfrozen region, is a part of a solution. So it's a free boundary problem. It's not given. And there's an extra boundary condition. There's instantaneous freezing at the boundary of the region. So I don't know if it's obvious, but you see, somehow on the outside boundary, since there are no constraints from one side, because this is the boundary, it means that the velocities can become ordered immediately. And this is what happens in simulations. You see that sigma is 0 on the boundary because, but there's no noise. You get this instantaneous ordering of velocities. So this is like so in some sense, these equations, well, these are rather standard equations in the theory of PDEs, right? The linear and the wave equation. But it looks like the free boundary problem and freezing are perhaps a little bit more interesting part for these equations. Now I have to tell you that I lied to you about the one-dimensional model. I showed you that simulations, but actually these are not the simulations of the model that I presented so far. You see, the one-dimensional model actually is different. This is a special dimension because in this dimension, energy packets are conserved. Namely, when there's a collision in one dimension, you just move velocities from the left ball to the right ball and vice versa. And this really, for all practical purposes, this is something like oriented swap process or colored tassa. So this is not the same kind of process because you see, in 2 dimensions, that it almost never happens that velocities are simply that the velocity would go from one ball to another. If you look at the 4 red arrows here, they are completely different. So we wanted to do one-dimensional simulations, and also, it is easier to work with one dimension. So we actually changed the model. And we introduced collisions of 3 balls, which is sort of not physical in some sense. But, well, it gives us freedom because now we have 2 equations because I want conservation of momentum and conservation of energy. But I have 3 unknowns. So if I have 2 equations and 3 unknowns, then just common sense suggests that we should have lots of options. And in fact, we do. We get a circle. And then I choose randomly the post-collision velocities on a circle, which is, like an artificial redistribution of energy in one dimension, so that it looks more like the 2-dimensional case or multi-dimensional case. And then there's this collision, which means that we reorder velocities on top of that. So what happens is that actually what you get in one dimension is nonlinear equations, or at least one of them is nonlinear, so it's the second equation. Then you do some transformations, and then lambda goes to infinity. Lambda here is simply the number of balls. And lambda in my simulations was between 1,000 and 10,000. So when lambda goes to infinity, you get the original equations. Well, not the original, but the equations the linear equations that I discussed so far. So the advantage of the one-dimensional case is that you can write some explicit formulas. By the way, an explicit solution to the wave equation doesn't have to have f and f. I did it for, to get a symmetric sort of solution. It could be f and g to different waves, sort of incoming and outgoing waves. But this is for the purpose of symmetry. And well, then one can assume that the spatial region that is unfrozen is non-increasing, or that is decreasing in time. And then the velocity, the terminal velocity, is simply mu that is frozen when sigma becomes 0. And then in one dimension, one can actually write some solutions. So you might remember that evolution that I showed you in Mathematica. And well, that's the analytic representation of that evolution. So here, let me say this. You see, in the middle, it is pretty clear that the mean is constantly 0. And it happens that sigma is a 10th function in, well, for this particular evolution. So, you know, you have an explicit, but there is no interesting freezing here, meaning that the whole interval freezes at the same time. This represents a more interesting freezing. So I'm not going to let you read this because, you know, I mean, this is just too much to read. Let me just show you the picture. So what happens here is that these regions over here freeze gradually. And in the middle, this whole region freezes at the same time. And I'm going to finish by taking just a little bit more time and showing you the Mathematica Simulation showing that. So first of all, let's just have a look at this. And then, okay, so let's go here. And please note that the end regions are freezing gradually. But at this point, the middle part is not freezing. It's just the noise decreases in the whole middle part. And again, it says the noise over the whole middle part is smaller and smaller. And then this whole middle region freezes at the same time. Of course, it's not perfect because we have some noise here, but you know, this is, I would say, sufficient good, at least from my perspective, or sufficiently close to that proposed theoretical model. Okay, well, thank you very much for your attention.
Thank you very much, Chris. Great talk. I like it a lot. Is there any question or comment?
I have a question. If you start, for example, in the one-dimensional case with a Gaussian field of initial velocities, and you do one collision, are you still in a Gaussian field, or the rules for collision break the Gaussianity?
Yeah, that's right. So the thing is that, strictly speaking, you're right, because after collision of two velocities, well, it cannot be, the joint distribution of two velocities on adjacent sides cannot be jointly Gaussian after a collision.
Oh yeah, because they cannot be against each other, right?
Exactly. So the idea here is the following. You can derive the equations for the moments simply by assuming that you are in the stationary distribution. Then that's what I've done. then you see what is the, you get a difference equation, meaning that you get the just the increments after one collision. And then hopefully the sort of the idea is that the system is mixing so fast that somehow after a few collisions, you're more or less in the stationary distribution. So an honest calculation would track not just a single collision, but a number of collisions, say 100 collisions in a neighborhood. And then one could say that after, say, 100 collisions, we are more or less back to stationarity.
I see. Thank you.
Other questions?
Hello, I have a question over here.
Yeah.
Oh, I think I know this guy.
Yeah.
Is this
because I have a gift for you right here.
Wow, wow, amazing. Hi, Julieta, how are you?
Great.
That's Chris. Do you remember him?
No, she
Don't
doesn't
remember him?
remember. She was too small.
That's my friend right there. Okay, you can go. So I have a comment and a question. First, it's really nice to see that you've seen finally like put into mathematics this wave phenomenon that you once told me many years ago when we started talking about these things. So that's great to see something that coming together. And my question is that when you do this maybe you haven't done this in more than one dimension, the calculation of the equations for mu and sigma. I remember that you once told me that, well, it's kind of obvious that that if you start with Gaussian noise, then you keep Gaussian noise forever because everything is a linear combination of the previous state in the future. But I wonder if you've explored more in more dimensions than just one regarding all these wave equations.
Okay, so concerning, Gaussian staying forever, you see, Gaussian stays only inside, when somehow when white, there's this part of the region where white noise is a reasonable model when we are away from freezing. Once we go to frozen region, I mean that Gaussian simply does not apply. So this is, this free boundary problem. And what happens at the boundary is, of course, a mystery because this is somewhere between Gaussian and frozen. So it's probably very hard. So Gaussian applies only in the bulk where there's a lot of noise. And then there, I believe it would be a reasonable, and at least in the simulations, it's a reasonable model. But certainly Gaussian is not conserved forever because of the boundary and freezing.
Sure. That's right. Okay.
But yeah, I did the calculations actually in 1, 2, and 3 dimensions. If you're asking about how I derived those equations, and actually there are some interesting parts of that I didn't talk about. You have to use the theory of frames. This is completely new to me, but like a sort of, it's not a basis, but a frame. Well, anyhow.
Oh, okay. Yeah. I don't know about that. Okay. Thank you for a very nice talk.
But thanks for coming.
Any other question?
Yeah, hi Chris, thank you very much for very nice talk. So if the balls have no radius, so wouldn't that be just non-interacting particles moving in 1D and getting ordered?
Yeah, that's right. So the one-dimensional case is very special because somehow the radii don't matter, as you said. And for example, this is the basis of all those extremely easy estimates because you just draw lines. And in one dimension, for example, the picture of interacting and non-interacting particles is exactly the same. So you count simply the intersections, and this is why you get n choose 2. So the one-dimensional case is very, very special. And this is the reason why we had to really modify it to sort of have like a toy model of multi-dimensional collisions in one dimension. Because otherwise, the one dimension has its own rules. So for example, I mentioned that, what is it called? Colored TASEP or whatever, right? I mean, it's a one-dimensional process. It is very special.
Okay, thanks.
So I have a question now. A comment first. In one dimension, your model was studied by Dobrushin and Sukhov and Boldrigini in the 80s, and they proved hydrodynamics for that. And then in the 90s, Boldrigini and Sukhov, they have some study of the second order. And then recently I was discussing this model with Spon and a student here, Grevino, and also Chiara Franceschini that is here. And we get that that white noise appears in the fluctuations, but this white noise of line process, like this Chensov model. We have not a preprint yet, but I was curious that you also have here white noise in this case, and I wanted to comment to you that. But also I wanted to understand the infinite volume model. So because one thing that you could do here is just to do the hydrodynamics in the infinite volume, right?
Yes.
Because you would have for the velocities any translation invariant distribution for the velocities should be invariant, right? For the dynamics.
Let's see.
Infinite volume.
But it depends what you mean in the infinite volume, because of course one could start simply by placing balls everywhere. So
Yeah.
not a finite.
In one dimension, in one dimension.
Oh yeah. One could have just one line, the whole line, and start with say velocities, everywhere.
And so you have some random distribution for the velocities, but in translation invariant.
Yeah, one could study such model. Yeah, so I didn't look at this because from somehow my point of view, it was that finite arrangements that were.
Okay.
But you're right, of course. And I would say that classically, lots of models in this area, right, of hydrodynamic limits are on infinite lattices and not finite chunks.
Yeah, because if you then have something that is not invariant for the velocities, no translation invariant, then you will have these waves coming right and down, right? They will meet and.
That's right.
We'll have, okay, thank you.
Okay, so I'm going to send an email to you because you mentioned a number of research projects and names. So of course I didn't catch them. So I will ask you for all those references.
Sure. Is there any other question? Okay. If not, let's thank Chris.
Okay, thank you.
Thank you very much, Chris. It was great to have you here.
Thank you very much for having me.